Okay, next integration method is integration by substitution, which is as near as we get to a chain rule for integration. There is no chain rule for integration. There is no product rule. There is no quotient rule. Integration is harder than differentiation. And the nice thing about substitution is that nearly always they say they will give you the substitution, which also gives away the method of the substitution, okay? And it is always a substitution we start with, okay? And I've been nagging you a lot about putting the dx on the end of your integral in class, okay? The reason for that is that the key step in a substitution is to turn an integral that just has x's in it into an integral that just has u's in it. And in particular, this dx at the end has got to change into du's. So that's where we start, okay? All right, there's a lovely tempting 2x plus 1 that you can see is going to turn into a u. Ignore that. Just get cracking on the substitution. U equals 2x plus 1. And we're going to turn dx's and du's into each other. So how are we going to do that? Well, we're going to differentiate the substitution. Whether it's u in terms of x or x in terms of u, which sometimes happens, you differentiate what you see. So du by dx equals, differentiate 2x plus 1. That's easy. It's just 2, which means that du equals 2 dx, okay, or dividing by this 2, dx equals a half du, okay. Now, mathematically speaking, this is complete garbage because dx and du don't mean anything on their own, but I'm not actually going to be using them on their own. I am going to be just putting it in to this bit of the integral. So that dx, I can see I can turn into a half du, and that's going to be the first thing I do. Now, this x in front, okay, that x there, you may be worried about, and people get excited about it far too early. Sometimes that x is just going to cancel out. So you just leave it there, let it mind its own business for now. The dx, our main business is to change that dx into the end a half du. Okay, now what about this bit here? Okay, well I could just copy it out. I'd rather you just copy it out than you try to do anything with this x here. But this is just obvious. 2x plus 1 is what u is. So I've actually got x times 2x plus 1, which is u to the power of 8. So it's very common to have a mixture of x's and u's, at least at first, okay? But quite often, we'll see this happening, the x will cancel with another x on the bottom of a fraction and we'll be really, really happy. Here that didn't happen, okay? So I'll have to go a little bit further with my substitution. All of this has got to turn into u's before I can do the integral. So I'll have to go back to my substitution and say that 2x equals u minus 1. So x equals, well, you might want to write u minus 1 over 2, but you know what? You don't want to get too many fractions embedded in this, so I much prefer a half brackets u minus 1. So I can say I've got the integral of a half brackets u minus 1 times u to the power 8 times a half times du. Okay, so it's all kind of on a line. If I did it the other way, if I had u minus 1 over 2, I'd get something like this, more scribble space. U minus 1 over 2 times u to the power of 8 times a half du. In fact, some of you might think that you'll get a du over 2 here, du over 2. Now, this is a bit ugly, all right? If you do end up finding yourself with something like this, and turn everything into fractions, including this one, u cubed over 3. So we can see we've got a half times 1 times a 4 on the bottom, and you're going to want to kick that out as a quarter from the integral. So on my version here, that quarter is this half here times this half here. So I'm going to bang down a quarter times the integral of something du, and now I can multiply this out. In order to multiply u minus 1 times u to the power 8, I'm going to do u to the power of 9 minus u to the power of 8. And that means that this substitution has given me an integral I can do. Okay, I wouldn't have fancied expanding that bracket out to the power of 8 while I was still with x's, but I've expanded this bit out no problem at all, so I'm going to have a nice easy integral to do. So this is what I want it to look like. If you'd gone down this route, then you'd have had your u minus 1 times your u cubed, and all of this garbage on the bottom, 2 times 1 times 2, the quarter. You'd have still wanted to kick that out in front of your integral. So now we've got to integrate then u to the power of 9, so a quarter is just going to sit there. U to the power of 9 is going to become u to the power of 10, and put a tenth in front of it, or u to the power of 10 over 10, I wouldn't have minded. And then this one here, new power of u, is going to be 9, and it's going to be minus a ninth u to the power of 9, and I mustn't forget my plus c. Now, I'm quite finished because I've got u's in this, and I started with x's. I've just introduced this u equals 2x plus 1 to help me do the integral, so every u needs to change back into a 2x plus 1. So the answer is, well, I can multiply this out now. No point in having more fractions than I need. So a quarter times a tenth is 1/40th, and I need u to the power of 10, but u is 2x plus 1. And the second bit is the minus 1/9 times 4 is minus a 36th of 2x plus 1 to the power 9, and I mustn't forget my plus c. So this, I'm going to box it. That is the answer. Okay. All right. So we've done a quite tricky integration by substitution. Wonderful. Okay, we'll do some more, but I'll do it in another video.